Hey guys, thanks for watching, and please hit that subscribe button, that little bell. If you're a member or you're a follow-up person or a new person, hit the bell also. That helps YouTube send you my data. Of course, some of the videos, if you pop in and you don't like it, give me a thumbs down or comment you don't like this content. That helps me also, but it helps me put direction to which way I'm going to go towards my videos. Or I take all negative feedback as positive, so in some form I take it as positive. I'm going to talk to you about today about buckling, Euler buckling. All right, so you guys can look it up, Euler. But let's talk, this has always been an issue with me, if you guys, let's go to the video, where I've always had it kind of odd. Why did it fail here and here equally across each other? How come there's no punching here? D1, D2 is so inefficient. How come there's nothing inefficient? How come there's no punching going through with the loads? Why did it break here? So that's always been I need to find why the loads resolve themselves from, at this point, going from 9 and 10, that's the bottom node, and making it over to the diaphragm. Why did it resolve itself here? And why not right about in the midspan between the two of them? Why did it resolve itself here? And I did a model video where I showed the nodal area. Basically, this is a gusset plate, and it's failing outside of the gusset plate, equally across the gusset plate, is how I describe it. Even though it's a flat flange, it's a gusset area, if you will. So on the other side of the gusset plate is the most amount of forces, the shear forces, I'll call it, right there. But it's so beautifully equally across, although the images do not show, which I need to get from OSHA. So I stand to be corrected on this if I can. The data shows otherwise when I do come across more photographs, and I'm not going to stop till I get more photographs of what OSHA has and what the NTSB has of the section they moved, specifically when it was laying here as they cleaned it up. You would think they would have done a saw cut in the street before they start jackhammering this apart, but apparently they jackhammered, while this was on the ground, they jackhammered this apart. And we look at, let me show you something. Hold on, give me a minute. Give me just a moment. You'll like the content on this one, I believe. So bear with me. So here's part of the recent OSHA report, and what I'm trying to describe to you is the underside here is missing. This is a saw cut. I would like to have seen a larger saw cut than this here, right here. This is a very small piece. This section here is hugely small. It is not beyond the break. The break is out here, but they show us this section that's it's almost insignificant. Of course it's significant, but it's not. It's controlling the narrative. This section is, because we don't go further out. Now this is where the section is right here. Basically what they're giving us, this section, that cutaway, it's right about here somewhere. But yet the bridge broke back here, apparently beyond the 10-9 node. We should have this entire section to look at, and specifically this part here. What I'm driving at is that I think, at this time, and I stand corrected if I have to be, when they jackhammered this, they should have saw cut this apart. They should have been removed with saw cuts, photographed, documented, like a real crime scene, like you're trying to find a crime, like you're trying to work it as a crime scene. But when you do this, you've now eliminated that I can only find an issue here, not back to here. This is critical. This is the load path failure. It's in a friggin' video, right, guys? It's in a video. And NTSB, OSHA, and everybody can see the video by then. It was released pretty darn soon before they started removing all the debris. Well, it was enough where they know, hey, if it wasn't released, they had it right there to see the break, that this is intact. There's a break here in the deck here. This obviously is a huge section that needs to be investigated. That there's no break here. In fact, since there's no video, you would investigate every single break every single brake and to affirm what each one is telling you. But they give us this little section here to do it. So I'm going to give you this word, one of my favorite things. I told you that I have a couple of favorite things I keep. Post hoc, ergo, procto hoc. Latin, which means therefore, because of this, is an informal fallacy that states, since event Y followed event X, event Y must have been caused by event X. It is often shortened simply to post hoc, which I also call it post hoc all the time. So, not all the time, I just called it something else, right? But I refer to it as post hoc. All right, so they did detentioning, so everything is related. The bridge is collapsed because of detentioning. All right, post hoc. Well, no. Let's each one. I told you the way I do it. I go, okay. Let's say if they're not related. Well, it is a progressive collapse, but I also talk about how initially in the staging area where they did the work, the staging area, the impound area, they had the cracks in here that developed. And I talked about in one of my videos that perhaps the scaffolding being perhaps the scaffolding buckled and gave just a little bit to allow for, when they were post-tensioning, to allow for some false forces. I've heard a couple of people write me saying, you don't know, I like to address them. I do post-tensioning. I don't like it. I told you guys I don't like it. I do love it and I don't like it. I don't like it for bridges. I do like it for redundancy, for external post-tensioning. I'm going to do some videos on that. I'm going to do one on showing a little 1/8 line. I came up with this little invention of for people doing 1/8 inch cable. 1/8 and 1-inch cable. You'll see it. I've got a couple little things I'm going to put out there, not for commercial reproduction, but for the general homeowner to possibly use, because someone else already stole a couple of things that I put out there for public use. Then they stole it and started manufacturing it, which was not what I was offering. So I'm making disclaimers now when I give away some of my little tricks, that they're going to be some of my little copyrights, if you will. And they are copyrights. So the moment you make something and you put it out there in the public, or you can prove its timeline, you own the copyright to it. You got to go to federal court to back it up, but you own it. So the patent office just puts it out there where someone else doesn't cross it from you, and you get to jump forward if you can. So right about here is where they did the saw cut, which is not where the bridge failure is. I mean, they gave us this little diaphragm section somewhere about here, but not where the rest of the data could help us. It is a punching hole. I spalled out probably from this member here slamming into the deck right there. So take note of that. What I just said, that member there, number 11. There is a spalled out piece, and I'm saying spalled out because I'm trying to let you guys understand that. So spalling is sort of like a martial arts thing. Imagine that if I punch here, like a movie, and this side, the force blows out this side. All right, so that's the spalling I'm talking about. And we look at it right here. See that the sun? You can see the sunlight on it. So that's probably where that member hit to be able to create that blast out there, the blowout on the opposite side. And there's our saw cut. So, it's pretty limited section here. And I was showing you over here, and I'm going to get to the post hoc stuff, how it all adds in. So bear with me on that. Bear with me. Right there. So right about there is that little bit of section they've given us, not the section that can go further out to where the video shows the break. All right, let's get into me and this darn break. Me and this break. So let's talk about I said Euler buckling, right? Euler buckling. Can overtensioning create failure? Can overtensioning create failure? It can. You've created a buckling, if you will. So let's use what we know from our plans, that this diaphragm is larger than this diaphragm, that number 1 sits on top of the deck, that number 12 sits over the deck. So using ad hoc and not post hoc, rather. Post hoc is ad hoc, right? So using post hoc, let's just keep these separate for a moment, and let's don't tie them together. So we have a local failure going on here because of the detensioning of number 11. The local failure exhibits itself as a crack like hell. So our local failure as a detension there. Now it's all a progressive collapse. It all adds together. And I'm going to get to the tendon shaping in here too. But right about here is where I think they should have kept it. The cracked. The break in that what we're looking in the air is right here. This is what I want to get more of. Back beyond this. This is the Jersey barrier break. So when it hit down, these cracks are from the Jersey barrier. They gave us a saw cut somewhere about here. Now what do you notice about that? Look at this length of this. It's pretty darn huge, isn't it? They gave us a saw cut back here. I theorized somewhere here. But maybe I have to shorten that up over to here even. And then what did they do? Blow it out when they were saw cutting? They made a mistake? Well, I'm saying they used that damn jackhammer to do all this demo work, and that jackhammer went too far and corrupted the evidence. It corrupted the evidence. They literally came to the removing evidence with a jackhammer. I mean, really? It should have been saw cut and removed away more. So my guessing on this YouTube channel, it's probably, not as I'll have to say, looking at everybody else's data, it's probably going to be the best guess you're going to find out here. And I need more data, so I would love to. I challenge anybody for that. And I'm not one to pat myself on the back with something like something normally. But this one, and it's sorry to say, I'm not happy to say that, is that I wish more people would tack NTSB report and the OSHA report and do more attacks. This is not right. This is not right that these engineers out here. And I went to the engine tips thing to look at it, and they had a link to. It's actually something I follow already. The FIU UK. It's because they do post-tensioning, and I do post-tensioning. I just don't. I don't feel like I have to give my qualifications to do my videos. You don't like it, good. And if you do like it, we'll talk about it. Talk about it. Challenge me. I'm willing to change my position. So any engine out there who wants to challenge me, and I'm willing to change. If I get the aha moment, please help me. Expand my brain. I don't suffer as most engineers do and doctors do, in that they make a decision and they feel they can't retract that decision. I can retract my decision and amend it. What happens with pre-stressing reinforcement? So, I follow all these articles. It was in here somewhere. The FIU, they talked about it. And there's one engineer there, structural engineers. This is structural stuff, see? He talked about it, but he was such a soft shoe that I found it to be just like all other engineers. Disgusting that they can't challenge and call out something. I just find it too soft. I mean, really, it's just disgusting. Point them out. It's like they're trying to protect each other like doctors do. Stop trying to protect each other. Create drama. Fight a bit. Fight. This is cut way to hell back here. We need the evidence way out there. All right. So let's go to, and I want to show you one more thing in here. So post hoc, these guys caused a collapse. The collapse, it was already a progressive collapse happening. I talked to you about overstressing. Can it cause failure? Yes, you created a load in this flange, a buckling moment. And I'm going to talk, and it's going to be very important, this profile they created in the deck also. And so are there any experts in post-tensioning? There are a lot of professionals. There are no experts yet. Like there is no expert on the brain yet. I'm sorry. So I take that back. I've mended my word from expert to there's another word I found. So you can be an expert, which means you're pretty damn knowledgeable. And then there's a gosh, I just found another word. Another word that shows that no, you are an expert because you like myself, you can find resources, find the data, put it all together, hand it over. There's one more level which says that now basically you're like the creator. There is nothing that can get past you, and so that level is the level that I'm stating that no one is of yet, and that was within the brain. The brain has not been fully mapped, so there is no expert of the brain at this point because the brain's not fully mapped. It's interesting, the brain. I love the brain. And how do they map the brain? They literally are taking slices now of the brain. I forget how many thousands of slices they're up to. And they literally look from one floor. And this I add into this, guys, so bear with me. So this is add into it. So they literally look from the bottom layer, and then they look at the layer, then they look at the bottom layer of that slice, a piece of paper, if you will. Look the underside. And you see a hole. Say you see the underside of a hole right here, where my mouse is, say it's right here. And then when you look at the top side of the paper, the hole comes out over here. So it's shifted. So that means you've already missed a lot of ways that the path that it's gone through now before it wound up over here. And that's a slice of paper, if you will. So they still need to get finer slices, and they just can't do it yet. So that means that the synapses could have gone up a lot more could have been taken place before it came out over here. And that's exactly what does happen. Unless you think the brain is that lazy that it decided that it needed to do a currency thing, it went that direction. And it could, who knows? All right, let's go. I don't want to, I like giving data and talking about the brain, things like that. Now let's go to, that crack. Hold on. Crack. Oh, scaffolding and crack. So I'm telling you where I'm going. So I'm looking for scaffolding and crack, small crack, at what now I'm referring to as a gusset. I used to call it a chamfer. This is definitely a chamfer, but I call the 8-inch a chamfer too, I think, per the plans. And that's right about here, this 8-inch. From here to here is 8 inches throughout the structure. I'm calling this a gusset plate now, this section. So imagine if this is a gusset plate, you now have a crack in your gusset plate. To get that crack in your gusset plate, you have to have a dip in your deck. You have a crack going across this section here, which indicates, and you have a crack here. So don't get all excited about that sliding crack, because this was still post-tension. This is 3/13, March 13th. This was still under tension, the deck. What if overtensioning, as I talked about doing D1s and then doing C2, and then tensioning numbers 2 and 11. And then they went to the rest of the deck, tensioning in that pattern. But over-tensioning causing the failure. All right, so you create, instead of looking at the tendon failures, think of the tendon failure in tension and compression, right? Over-tensioning of them, creating a compression, zones that are excessive. And why do I reach to that point now? Why do I reach that point? Bear with me. I'm going to say it in just a moment as I bring up the scaffolding. So think over-tensioning. I need to see more details of this. If I can get this thing to lift somewhat, I can explain all this in over-tensioning also. So bear with me. Gosh, I could explain it so much more. This is on 3/13. I'm sorry, the bridge died on the. So that was wrong. That was I needed something before March 10th. Sorry about that. A couple of seconds ago. Let me amend that. Let me go back. All right. So this is the cracks like hell I talked about a minute ago. But I got to amend my those cracks we identified. So going back in the video where I stated, and I'll amend the cracks too. Hopefully I won't forget, my brain won't forget. So this is the post hoc stuff, right? So the post hocs, the guys are on the structure post hoc. Ergo, that one happened causes the other. So because they were post-tensioning caused the whole failure. Let's just think of this locally and separately now. Don't tie them together. That detensioning 11 caused this failure here. Progressively, it would have caused the collapse, the structure to fail if the failure would still, if it would still tear apart. So right now, if you could stop things in space, 100%, if you could stop time, this is stop time, we have a snapshot of 3/12/28 that the bridge did not collapse upon detensioning number 11, A and B. And this is what that snapshot looks like. Now, progressively, through creep and through the loads going to keep coming downwards, they're going to progressively cause failure. This will go to the ground. No one will argue that this will eventually creep down to the ground. All right, but it didn't happen yet. So detensioning didn't cause the immediate failure. It caused another step in the progressive failure if you just left it alone right now. All right, we still have all of these tensioned at their whatever they were. They did not go in here and detension them. So either these are elongating, which means they're getting more stress on them as they're being. So these are going to the ultimate tensile strength failure because the deck, they're still holding the deck. Yet we see not one of these in the impound popped off. Not one popped off. So no cable popped internally. A group of cabling, and then worked their way through the clamps and came out through this little plastic shell, including grouting inside there, if it was grouted. Incidentally, I see no evidence of grouting. I don't see any poured down grout. I mean, these guys did an awesome job. They plan on closing this up afterwards. This was going to be closed up. I'm being facetious, so you know. They planned on closing this up. And yet, not a speck of grout on a bolt head. And they said this was grouted. Nothing. I mean, they do an awesome job of cleaning up. Where's the grout? Not a speck of grout on the outside. I mean, they just vacuum sealed this thing. I mean, it's just awesome. I'm being facetious. I mean, there's no grout around this coming out of anywhere here. So I find it to be not... Okay, so I'll bring in my policing stuff for you guys. I find it to be unfounded to state that OSHA states that this was grouted. I cannot find any evidence that shows that it was grouted, so I find it to be unfounded that these were grouted. At this point, now that means I can change if you show it to me. I mean, there's not a speck of grout on this damn thing. There's not even any spillage of grout on the face of this. I mean, they're just friggin' awesome. Facetious as can be, and I would curse at this point with my description. Because in the real world, I'd say, where the F is the grout? How come you guys cleaned this up so great? You know, how is that possible? Being facetious. Moving on. I'm triggered myself on that. Let's move on. So the bridge moves, and let's talk. Let me do one quick attack on Engine Tips, the Earth guy over there, because he attacked me. And then, he stated that the bridge was placed in 2 locations, moved in 2 locations, and put down on 2 locations. Well, he says he's a structural engineer from another country, and Engine Tips agrees with him, obviously, that he's a structural engineer from another country. So it's placed on 4 shims here, 4 plastic shims. It's moved on no less than 8 locations, not 2. It's on the other end of the structure. It's placed on 2 locations. So I've got it replaced on 6 locations minimally. I've got it moved on 8 locations minimally. And minimally because if the full shimmed blocks were not fully shimmed, rather, if they had spacing between them, well, that's a space. That's another point load doing transportation. It shall not be discounted. All right. So the bridge moves. We have no failure at this point. It's placed. We have no failure at this point. They detension. We then see cracks show. We do have cracks in there. Let's go to the cracks real quickly. These cracks that present. And so I find it very upsetting too that those structural guys over here I find, structural engineers in this entire group to suck. I do look at all the data. I look at everything I can. I'm always reading it. I find them to be suck also over here in the Institute of Structural Engineers. They did not, he said he looked at all this stuff and yet he didn't say that the photographs show 4, 5, 6, that he used it as supporting data for his video there over there. And yet, he did not state that he did not show the inconsistencies in the report. He was all on board. Because what happens if, as an engineer, you show inconsistencies? Nobody wants to hire you. They're like, oh, you're going to be trouble. We don't want you. You're going to be trouble. We don't want you. We're not looking for trouble. We want somebody who's going to go along with the program and make it most cost effective. So they don't want you, your personality. You can't rock the boat no more than a doctor can. The doctor starts rocking the boat saying, we're prescribing too much medication to these people. That doctor's looking for a new job. So all engineers, so a structural engineer is nice to get some data from. But only if you can, because once they make a report and you put your name on it, that's out there now. That's done. So they're just like a doctor. They're worried about their name being out there. I think it should be mandatory to help with structural engineering and doctors. It should be mandatory that you write at least, part of continuing education, that you write at least 5 or 6 critical documents a month. So that means you're looking for problems. And I'm talking about per month to maintain it. So your continuing education, you will post 5 to 6 critical documents of the environment that you're in per month. This will be, period. And that's how you learn. You can't be all supporting. You can't be all pats on the back. This is the crack here on 228. This crack is identifying a very interesting thing. Perhaps the overloading of the transverse longitudinal cables, right? So let's go to longitudinal cables in the stack. They were post-tensioned and designed already to take the loads of all these, the weight of the pipes, the 1 1.25, they're huge steel pipes, right? 1 inch plus, thick walled. We're talking, hundreds of thousands of pounds up here on top of this deck, including the dead load that was not installed yet. So these cables, these longitudinal cables, were designed to take all these loads. Yet they already tensioned the deck fully when they did the transportation to take these loads already. To take the loads already. And then they added number 11 through FDOT, adding number 11 post-tensioning in here. So you have this compressive moment in here by the transverse longitudinal cables, a huge compressive moment. And then to top it off, so you imagine how tight this is. Just imagine this tight band right here, this tight piece of member. And then I add at the ends, right here, I tension number 11 and number 2. It's already tight, and then I grab my hands and I pull up the bottom of this band here and here. I put another force here, a moment here and here by tensioning number 2 and number 11 into the hundreds of thousands of pounds of kips. Would I not create a bending moment? And where would that bending moment be? How close, if it's bending upwards, where would it bend up? Would the fulcrum, if I'm bending here, right? Would it not be pulling between here and here, creating a bending moment upwards? And would that not resolve itself in the deck area between here and here? If I would step on a 2x4 or step on a soft piece of plywood. So your foot is here. I want you to pretend like this is your foot. And I want you to pretend like the other end of the plywood is here, your hand. And you're standing up. This is your head. And now I want you to lift that board up towards you, towards your head. But hold your foot down right here. Where would you create the moment? It would create, between here, wouldn't it? And if your foot is here, wouldn't it more deflect by your foot, that nodal area of your foot? So I am stating that I think I'm now figuring out why it broke transversely across this deck so evenly, that why no punching happened, even though D1 and D1s through D6 are of different post-tensioning. D1 being of a lower post-tensioning than D2 through D6. And yet it still broke evenly across. And remember, I argue that Denny Pate did an outstanding job in his engineering, that these things did not fail. Including this did not fail. Including this did not fail. That all these other engineers and engine tips, we'll call it, because I could not find the critique anywhere else besides engine tips. And frankly, I love a good argument, a good banter, and I do look for a good banter, but not stupidity, as they are all the engineers over there, except for a couple of them that are following me, and I find you guys to be awesome, right? Of course, I'm going to say that. But I hope you are able not to get back to the brain part. You have to let go. You have to let go. Let go, and I do things like, so this is some of this one here. If you really do something, if you really want to do something, you will find a way. If you don't, you'll find an excuse. So this is one of my mottos, excuse, and I found this tab. Excuse is holding you back. You tell me what you're not doing, and I'll tell you have an excuse for it. You just tell me your excuse. You have an excuse for not doing whatever you're not doing. You're not losing weight, well, you have an excuse. So just tell me your excuse, and I'll tell you, well, that's what's holding you back. Well, all the engineers that don't speak up against this, they have an excuse. Just tell me your excuse. You're like, well, I can't because my name. All right, that's why you can't do it. So that's it. So create now let's use this as the fulcrum. This is your head. This is your shoulder. Rather, no longer your head. This is your shoulder. That's your arm. That's your foot. This is the pulling of the tension created during the post-tensioning. And yet we have blast off. You know, I'm taking liberty of my wording now, right? So you're pulling here. Number 12 is already defective. It's already defective. It's already defective in design. So I have to edit that in my brain because quickly my brain ran. It's not defective in design. It's defective in, at this time, the post-tensioning being added. Because we saw it move and it didn't fail. We saw it move. So it's defective it's defective in that they're using, it's not defective in design because it moves, right? It moves without failure. The outside of this image video. So page 45. Let me write this down because I got to come back to that with my comments to you page 45. All right. So it's not very good. It's not defective in design, even though I critique it and others critique it that there's a pipe through it, etc. Do you see this falling through at this point? No. So we you know, I don't throw out the baby with the bathwater. I told you guys this. So everybody I dislike, I also find something to like in them. So if I don't, so I may not like, Denny Pate with his cockiness, his attitude, his careless, the lawsuit, defending himself. Clearly he should. So I should not dislike that. What I dislike, and I'm going to do another video on, is that, really you're just going to go on like a medical doctor who kills somebody through a mistake and goes, hope they don't find it. And my insurance will pay for it if they do find it, and I'm going to keep on practicing. Where else do you get to kill people and keep on practicing? In engineering, and also in medical field. I can't think of anywhere else in like a field where they protect, where you're allowed to, where you're supposed to protect the public, not a cop or anything like that. Where the trust is in there and your skill set and all that. And when you do kill somebody because of your design, it's like, yeah, my insurance will pay for it. Plus, you know what? Maybe they won't find it. So this held up. But this is that crack I'm talking about. It came across here. And if your foot's here, and this is designed so well, and the loads transfer equally, if I put down my foot here, the loads will transfer equally across. So I get my lateral crake. Yeah, what the heck? I'll just say crake now. Crake, C-R-A-K-E instead of C-K-E. You get your lateral crake. Oh, wow. I shouldn't have joked around. You get your lateral crack coming across here, transverse crack. If you look at the bridge failure, it appears to be a transverse all the way across. I mean, it didn't break here, punching through apparently, and it didn't, if you look at the images on the debris, it appears to break equally, parallel from each other, from this side to this side. So I don't get this punching thing. And so therefore, if I don't get the punching thing, I cannot claim that D1. And see the way these located, D1 and D2 are lower than the rest? This is a profile. But yet, nevertheless, this profile didn't create a weakness where, okay, it broke like, I don't have the images, where it broke like a V, where it came in and then broke upwards. I wish I had more photographs showing that, but apparently that might not even happen. So what I'm telling you is that, or stating that, this, coming across, I have a full break coming across. So that means this nodal area and this design is still awesome. But, here's a but part. Can you get failure by overcompression? Of course, you're overloading it. So if all of these are just already capped, and this is a done deal, and the OSHA reports state it's already been grouted, that means they're not going to come back here and open these up and retension, because it's grouted. There is no rebite at the apple after you grout, without some structural issues. So we look at the word grout in the report, and it says, except for diagonals 2 and 11, all tendons and post-tension bars were grouted in the deck. That's 1 of 6. So that's it. So this is a matter of fact. So this is my as-built. Remember I said I wanted as-built? Well, let's use OSHA's statement here as an as-built declaration. Okay? So I'm sticking with that. So let's go to page 45 because I said I'd go back to that. So I'm stating that it's already been maximum tensioned in this deck, which means compression, which means possibly buckling, which means the weakest point being resolved how? That when you put your foot down and bend up on that plywood, it breaks by your foot. It doesn't break by your hand, does it? So we now get a new force that could be doing all of this crap. So we in the staging area, could that already be taking place right here? And of course, my scaffolding would show that deflection because you would still get a downward moment at that point, at that scaffolding. And of course, if they took as-built using a surveyor, a professional surveyor, then they would see the deflection in this deck. And this is amazing that this, and I want to curse now, that this person shouldn't be practicing anymore, or there should be some major stuff here, that critique thing, that this person should now have to critique what he did wrong with this structure and put it out there in a public document. And if you can't critique your own work, I mean, come on, guys. I critique my own work all the time. I did my little inventions and I critique it, and I know that I can do better on my inventions. It's just a concept one when I do it. For example, I'm going to show you that little tensioning device I use with the, I don't want to say it because I didn't post it yet. So I can't say how the design is because someone could quickly watch this video, do it, post it, and then they own it before me, even though I have it already made. I wouldn't be able to prove that I made it. Oh yeah, I have a video, and I don't know if it's time-stamped. So yeah, I can't do it. But my point is, I could have stepped it up a lot better, but the concept is there, and then any rendering after that still belongs to me. So as long as I get the concept out there and someone makes a better wheel, if you will, it's still my wheel. And all right, so could this be, as I just stated, your foot's down on the deck? Because this is 228. And this creates that creep in the deck. But a problem with the creep in the deck is that I have multiple, and per this report, we have multiple engineers, FDOT, FIG, FIU. We have OSHA using multiple computer programs. No computer program shows failure between 10 and 11 at this point, at 228, this crack. None of them show it. None of them show a sagging of the deck. None of them show it because they're possibly running the whole computer program, possibly running it. We don't know because they don't share when they ran a computer program. The computer model, did they run the computer model with the whole bridge built? Or did they run a computer model with just this section here without the loads on it? If they do it in the end, did they run it with the cracks involved, the model with the cracks involved, and then add the post-tensioning? I don't think they did under OSHA's thing. I don't think they added the cracks. And I don't think Denny Pate did either because they discount all this crap. All of them do. So what I'm just showing you is I need to do it uncorrupted. Uncorrupted, but I do corrupt. I do take the data on. I'm always fighting myself internally in my head. All right. So now you have these transverse, these longitudinal cables, post-tension, and so they're equally loaded here. But cables, and I'm going to show videos. I'm going to break out my post-tension gear on you guys. I got to do it safely though, because you got it in concrete when you post-tension. The failure, is limited to pretty much ejection. But if I'm trying to show you out in the open, that whip, the cable breaks in the middle, any of the cables break. You just need one cable to unwind, and it won't unwind and come back at me, but it'll break, might break next to me, and it can unwind to some degree. But if it was to break fully, if it was to ultimately fail fully, that cable can come back and end my life. It whipped me right in half, and that's it. I mean, it cut me right in half. So I will do it to some, maybe 20%. I'll take it up to 20%, something where the cable, and I'll break out my good gear on it. I got to make an abutment on each end to do it, to show you. And then I'll show you that we'll put loads. We'll put a steel weight, simply a 50 pound steel weight, and then we'll run another cable parallel to this cable, not touching this structure here. And I have to use my transit to confirm that it's flat, so you can visualize it. Then I'll load my weight down the cable, and you'll see that it's more that the cable will not deflect as much as it deflects in the middle. In other words, the cable here in this bridge is it has different forces. This end has a ultimate. I'll show you in a minute, but let me talk to you first. So this end, say let's go 100,000 kips, right? 100,000 pounds of force. And then let's say this end has 95,000 pounds of force. In reality, this really did happen. This end has more force on it than this end. And that's because that's just the way cables are. That's the way they are. The pull you're pulling on creates less or more, whatever it may be, however it works out. But there's only theoretical, because they cannot go back into this bridge and test the tension in here. It was a Texas one that did it, and it was kind of awesome. But they didn't share all their data showing it. Hey, when this was post-tension, do you know it's only 40,000 kips here, and then we go another 8 feet, and now it's 45, and then we go 8 more feet, and now it's 46, and then 8 more feet, 46 again, and now we're at 50, and then now 100. It's a weird scale that changes per the profile. In this case, it would be related to this too. I know this is a long video, but bear with me. Why? Because let's just talk about the deck, the canopy. The canopy is uniform in shape and design. The canopy is uniform in shape, rather, and not design. Because by design, the blisters, nope, don't put the bars on them yet. The blisters are not located equally apart. So the blister weight counts. All right, so uniformly, the shape of the blister is uniform. I mean, of the canopy. But the blisters are not. So you'd have to add this as a load. So you decide, figure out how much the blisters weigh, and they are hugely different in size. They are big loads. And then we have to add and then let's do another thing. So the deck is also uniform in design, not the diaphragm. The deck is also uniform in design. So it's going to be equal loading on the cables, and on the canopy it will be equal loading, not counting the blisters. So let's keep that as equal loading. But then they added these concrete members. So just add them as equal dead loads, not truss systems like the engine tips people do. And I'm attacking them, yeah. Because I find all those structural engineers, they're lacking. You can come over here and challenge me. I find you all lacking to consider as a truss system. I find you to be inferior as a human, because you can't use your professional knowledge to change your position that this is not a truss system. And so, wow, isn't that an attack? That's a super attack. So you can attack me back as a human. I find that pretty darn aggressive on my part. So I take that human part back. I'm just trying to give the most attack I can. I find you inferior as I think you should find another job, is what I'm saying. I find you inferior as a human to take on a job dealing with any engineering if you see this as a truss system. So we have a canopy, and so we got a flat plate and a flat plate. And on that flat plate, they ran these concrete members that have a dead load weight. So these are loads on an incline. That's all they are, just loads on an incline. They have no ability, they should have no ability to act like a truss system, as Engine Tips calls it. But let's reverse that, in fact. I know, guys, you got to bear with me on how I talk, how I present. Let's reverse that, in fact. Well, if it is load on an incline, let's just use this one here. If I were to put a load here, this would just fall to the ground. So just use this one member here, right? Just look at this right here without this being here, this upright. Well, let's use this one. And let's take away this upright here. If I would put a downward load right here on this member here, what would happen to this? Don't add these in. Just put a load there. Well, this would just, if I put a load on it, would just fall down. The securing point on it would be here in this ground, in this area here, would stop it from wanting to fall over. But it creates what they call a moment here, and we don't have to go down that path yet. Let's pretend like this is secure and it will not buckle down. It will not create a sag here, and a break and tension, compression. It's a cantilever at that point from this point, but I don't want you to think of that. So just the load down, it would just fall down. Well, what would stop it from falling down right now? Well, if it was sitting on top of this upright right here, this would then transfer the load. So I'm going to get us a better image. So bear with me. You're going to still like this video. It's going to give you, this is probably going to be one of my better videos on helping you understand what's going on here. And I'm looking for the diagram, this resolves it for the truss system, and all the stupid engineers that want to consider this a truss system, but also will put back that perhaps it has no choice but to act like a truss system. Watch that. How's that for an attack and then a reversal? So here you guys go. Which I did in a video a long time ago anyway, where I talk about it. The loads, having no choice, loads on an incline. I'm looking for the truss system. There we go. So let's use this one. That's the same one. So this is the way it comes up. Is number 4 sitting on top of number 5? Or are they encompassed together? It was a single pour. So they're encompassed together. Number 4, I could theorize that this is the nodal, the gusset plate area, and that this could go that far. Does it go across number 5 and sit on top, or does number 5 go all the way up and this sits on it also? Well, it depends on the load. Where do I put this load? If I put the load here, all the load goes down 5. If I put the load on this side, so imagine a line going up here on this side, well, the load comes down and creates the transfer of the load is directly downwards, creating a shear point here. But load on an incline, it would also come down on a 45, and it would have a moment of wanting to push this over. But mostly, this is plumb. Mostly, it's not plumb. It's on an angle, as you can see. It is on an angle, but so it would have like a slight kicking out effect, a torsion right about here. A moment, but I help you guys understand it, like a torsion effect here. It's like you're leaning over a little bit, and I have you hold a weight. And what happens if you hold the weight when you're leaning over? Well, you want to stand back up. And if you lean over just a little bit, it creates more stress on your back. So that has a little more stress on its back, if you will, depending on where the load is. But let's use that there's only dead load, no pipe here. So the dead load we're talking about is however it is, however this translates to all of the rest of this canopy to here. And I can't translate it for you guys because you just can't without knowing all of where the cables are located in this, and how much load are they really transferring down here. You need to know how much the transverse cables are load they're transferring. If you can remove them, just clip them with a pair of scissors. Now you can calculate the dead load of this just by dead load. You add up the concrete loads and you work your way down. But it's not going to be that easy again, because they're going to create a moment inside each one of these differently throughout this deck. And we won't talk about that. Let's just talk about this for a second. Let's pretend like you could clip the wires and this is just dead load. And that this is just solid steel down here. This is equal steel, no transverse cabling in here. This is solid steel at this point. So now we just have dead load. So let's push this load down. If we push down on this, some of it, like your back, is going to want to push this direction and create a tension, compression here, a little tension here if the load is coming down. And it's going to create tension in here, actually. It's going to want, if it's pushing down, since it's going to try to push away, to stop it from doing all that, we have a gusset plate, this concrete. So it acts as 1 now. So if it acts as 1, it now will just push down 5, and it will go down 4. Load on an incline. And as it goes down 4, the loads will want to create a buckling somewhere, possibly right about here at the top. Usually buckling happens on the loads on the columns at the top. Sometimes they happen at the bottom, depending on how they did the reinforcement. Did they lap the lap joints? Did they lap it in the middle? A lot of people lap, a lot of these engineers lap their columns at the bottom. And so a lot of times you'll see the buckling at the bottom. And they'll change over the bars. The main bars will go from, down in millimeters. And so there's the weakest point. So it depends on the steel also. But we didn't have buckling here. So I'm talking to you about the loads. So the loads are coming down here, and whatever loads, the dead load. It wants to push this away, right? Because it's encompassing here as this triangle. It encompasses this next gusset plate, this next concrete nodal area. And the next gusset plate will shape with that 8-inch. See, that's 8-inch. That's kind of like this, and this is the gusset plate. So this would be like a gusset plate here, gusset plate, gusset plate. So as you try to push a load down here, this wants to push this one over down, and it tries to push it out. It can't, though, because it runs into the gusset plate and the reinforcement, if you will, in here. So it can't push it out, but it still creates a moment. It's still there. A force is still created in there. But none of it identified itself. None of it is shown in photographs as identifying itself as actually a movement. So we have no real failure of this acting like a truss. So even though this dead load is here, it shows no failure of acting like a truss system there. They show no gusset failure here by showing cracks here. They don't show it here. They show it nowhere inside besides a couple of these members here, number 3 and number 2. They show it in odd places coming across number 2 when this is in the impound yard, in the staging area. They show it across here. They don't show it, and they show some here, right, in this hinging. I'm going to stay away from that end. They show it here, coming across 10 rather, here and here and here. Now, I stated to you earlier, if you put your foot here and you start tensioning 11, you create that flex, or like the plywood coming up. If that's the case, didn't you not create compression in number 10 inside your body? So how can you have a crack, an opening crack inside your body if you're now taking loads on? So then you see I take a different bite at the apple. So at one point when the guy photographed it, he was not there during the process. And being not there during the process, he didn't see it develop at what point these developed. He saw it days later, and I think it might have been even weeks later. I think it might have been, tens of days later, or should I say, 5s of days later. Groups of 4 days or whatever. It might have been 14 days later, or 13 days later. I'm trying to say weeks. I'm trying to control the narrative, I guess, by saying it was quite some time later that he saw it. By then, perhaps there was no cracking in here when this was tensioned. And then days later, the scaffolding settled. So we have to show you the scaffolding now. And then when the scaffolding settled, we see the creep develop in the deck. That a crown possibly was created in a canopy. A crown was created in a canopy this way. Remember I said I like to see a crown in a canopy? Well, maybe now I have my crown, because also I have a huge bending moments in post-tensioning right here. So a lot of these guys, engine tips, and in fact, the guy I'm going to attack again, Earth, claims to be a post-tensioning guy. And all those guys over there, it's only him that claimed to be the post-tensioning guy. Well, I call bull BS on him. Because he should have been talking about the moments inside here. And I wait. I'm an experimental guy. I will watch and wait and have data sitting by to see if anybody else is going to say it first. And they do, I jump on it. And so I love it. So right here we have the post-tensioning coming across here, but we have a bending moment upwards here of the post-tensioning, a force that it wants to push this up. And on this one we have a pulling down. So what do you have? You have two guys wanting to pull away from each other. Right at the point we have a separation here. This is critical. This is critical. Let's look at it. And I mentioned it in my video days ago about that. And now it shows up. And this somewhere here. I can't even find it now. I looked at the video, and now I can't find it. No, it showed up in a post-tensioning description video. I had an engineer that likes post-tensioning, which was good. Oh, right. So we have this. This is the deck, and this is the backspan. This is not the other one, but the profile is about the same. When you're tensioning this, it has a pushing down effect. So, So if I just imagine it's just as anything you can, you know, like a string, a cable, anything you can in your mind that you have. Pull it tight in one hand and the other hand, and then put your tongue out. And put your tongue near the end, or this one, and then push it up by whatever you can. You know, push it up by 2 inches and and let your hands relax a little bit. So the string is creating a profile across your tongue, and your right hand is here, your tongue is up here with the string across it, and your other hand is down here, equally like this one. All right, so this resting kind of laxed, right? So now imagine if you do not move your tongue, and you started pulling these cables tight. Now pull your right hand and left hand away from each other towards the outer space, away from each other, parallel away from each other. You will create a moment pushing down on your tongue that wants to cut your tongue in half. You can't move your tongue. Well, that's the same thing that happens in this concrete. It has a downward force right here. And the same thing with the upper part of the canopy. It then has, this is the canopy, albeit it's a small radius, and they calculated for it apparently, but it's still a force that's using up energy and when they post-tension this. So when they post-tension C1 through C4, and if they do C1 and C1 in the deck, C1 initially, they do C2 initially. Two longitudinal marked previously were made for the May 10 to mark C2 and C3 to provide later. Longitudinal tendons marked C1 were provided with, right. See D1, so temperature is very critical too. D1, that's 2 D1 left and right. D1 was done on the 23rd. D1L, right, and D1L was done on the 16th. Days passed, so the symmetry in the structure it's no longer, I mean, it's like simple engineering. You don't do this. You don't, post-tensioning is a crazy thing, right? It's not, there's no expert on it yet. But theoretically, you have to have a theoretical mind. What happens theoretically if I post tension D1 left on the 16th, and then I wait 5 days to tension D1 right on the right hand side? What happened? What happened to those forces in this deck for 5 days as it was applied? Did it not create changing, since you didn't do it symmetrically the same day? Did it create some drama inside the deck? People say, no, yeah, that's not, no, it didn't do a thing. Well, let's think about bolts and tensioning bolts on a vehicle. You do your car rotation tires, and they tell you come back in so many hundreds of miles, and we'll check it again. Well, why do you have to come back? Because things do change. They slack and they change. And you didn't do this symmetrically. You didn't come back and double check. I don't see any double checking here. D1 and D2 were done days apart from each other, and then no verification of D1 to see if it changed at all. It's just using extrapolation and saying, nope, D1 is going to be a solid deal. It's done. You don't have to do anything else again. D1 is done. We don't have to go back and check that again. They're just too cocky, these engineers, with this post-tensioning. I've used all types of measurements on my post-tensioning, checking it out. And I tell you what, that thing's changing all the time. All the time. And especially if you go look at the one I found in Texas. It's beautiful, that long-term vision of it. They show it month after month. The profile tensioning of that structure changes because they had the embedded tensioning software, hardware into it to read it from software. And you could see it change all through the day, through the night, through the winter, through the summer. It just changes. This is a fluid bridge. Post-tensioning is. Cabling is very fluid. You can watch cabling slack everywhere if you just look at it everywhere. Just look around at railings, cable railings. They go slack everywhere. I install cable railings. I think they're beautiful when you install them, but you can watch through the day as it goes slack. And then the next day when the sun hits it, it's no longer slack. So this thing is going through all types of drama. So we have some elongation just by the heat of it. And then we have a cable that was not temperature. They did not take a temperature of this cable before they started elongating it, of the bar, before they elongated it. I mean, I saw nothing of that. OSHA guy is not a post-tensioning expert, obviously, and I hate to attack him because I'm going to ask him, try to talk to him, get more data from him. So please, if he's watching this, please, work with me. So you needed to get more data, such as what temperatures were the bars when they started post-tensioning. What temperature were they? They're going to react differently. All right, maybe I can show you that. I'll heat up some damn post-tensioning. I'll put some PSI on it. You'll see that thing elongate differently from a cold bar I'll put in the refrigerator. And we'll see the different elongations with the same PSI. I need to wrap this video up. It's probably 40, 50 minutes now, right? What are we at here? 1 hour. Terminating video. Oh, man. This is way too long. Way too long. I'm going to do a part 2, guys. You need to see part 2 of this. But I think I'll just... darn it. You need to see part 2. I'm going to explain the compression again, but maybe you'll start... Maybe some of my brilliant engineers out here will start catching on and start seeing the compression failure, and as I stated, with the foot and the bending moment created by pulling up on number 11, creating that downward force. I was trying to show you guys that downward force down number 10. Once you started putting the forces on number 11. And showing you that how you can explain a lot of the cracks now. Let me race through this. Now this one I'd be proud for NTSB to take some data from. This one I would be proud from. The others I sort of trolled NTSB, and everything else. But this one I would be proud of. I love the yeah, whatever, haunch, the haunch material here, the haunching, the 6S01, is that it? I can't read it. This is a little haunch, this is a chamfer. The haunches are cool. I was going to do a video on haunches. This is, they're usually using dams, etc. This is what's discounted by a lot of the, that no one's spoken of in those engine tip guys. And I find that kind of weird that the guys are, I'm not claiming to be the structural engineers. They are. They're claiming that. I find that lacking on their part again. They're not talking about the reinforcement up here. That it's good haunching. Haunching. The D1, and anybody, you guys follow me over there, you know, obviously I don't want to attack you because that would be attacking a good supporter. So understand that. All right. So, and I'm going to unblock a couple of engineers I blocked that were trolling me. And if you troll me again, I'm just going to block you again. I'm the only one that's going to see your comment. So I'm going to allow you to comment again. If you can't get over yourself with attacking, if you can't get over yourself, I'm just going to block you again. And also support your data. Just don't come in here, throw a punch, and try to think I'm going to post that. I don't throw punches. I'll leave you a punch. So if you punch at me, I'll leave it. If you give it support. If you support your data, then I'm definitely leaving it, giving you a thumbs up and a heart. So, you know, don't use your stupid, idiotic comments, such as that. I don't want to hear generic, that doesn't follow, or don't say, you don't understand load path or something like that. Don't say something stupid like that. That's just a stupid comment. Just tell me what I don't understand and show me your load path. Then I might go to your load path. My load path, if you don't understand it, you show me the defect in it, and I will post it. Even if you're wrong, I will post it, and I will troll you back. Go out and show you the defect. So don't be a little scared chicken. Don't be a little punk AS. You know, bring it on. And you see, guys, I'm from Philadelphia. I'm not these guys. I don't know what most engineers. Most of them have a self-esteem problem, and that's just a weird thing. Like doctors have a self-esteem problem too. All right, and I date a lot of doctors. So here we go here. But they do think they're God. They have a God complex, pretty much. So we have. I think this is the failure then, because it appears to be sticking off the deck, and D1s, and this is that break I talk about. I don't see the reinforcement, the punching shear reinforcement, the reinforcement going across here. We don't see it, but we don't see a butterfly of this damn deck folding over too. So we all can claim that it's weakness in the center line, but we don't see it happening. We don't see a split down this deck happening. And it clearly should have happened at many locations. So thumbs up to Denny Pate and his engineering on that. So sorry, guys. You know, you don't throw the baby out with the bathwater. The engineering awesomeness is here. The Denny Pate could patent this design here. This worked. This part worked, guys. This worked. There is no haunching material here. This is sort of a haunching deal here. Not correct. No, I take that back. No, it has to come on through and dissect like the other one. You guys look up haunching. You know, you'll like haunching. You're like, oh, cool. A couple of my guys that are really like Dawson them. Maybe I'll do a video on haunching. Maybe I should just click open for you guys on haunching. But all this crap worked. This worked. So the failure is the okay. This is what I want to show you. This is the tensioning, the longitudinal cable and the canopy, and this is 99 feet. So this is the back span. It's the same as the other span. They do a jog. This creates that tongue effect, tongue and tongue. All right, and you can't get around the tongue. And then it also matters how they did this radius, how they put it in there, because this might create a wobble, a friction against the walls. It definitely touched the walls. There's no freebie here. You're not going to pull a radius without it wanting to straighten out. And so you're creating a moment, a loss of your forces in the change of angles. It's period. You don't get away with that. It's a fact. You don't create it. You don't get away with that. Not. Now it can always work in your favor if you put it in there for that reason. So because you're countering those forces. So we can talk all the crap we want, but it worked. All right, I'm going to find one more thing for you. So adding and moving the location of the transporters, but adding number 11. So I want to throw F dot not fully on there. So don't. It's not a fully attack against F dot, but it's a full attack against not understanding your structure. Is that you need a nut job like me to go over to be part of a job, because I do it. I'm gonna probably lose an engineering friend because I'm gonna post a video for you guys on this structure. I'm gonna hide him as best I can, but if he sees my video, he's probably gonna get upset at me. I won't lose him, but he asked me not to share it. But I'm gonna show you a new bridge with cracks in the structure, and you guys are so smart, you're gonna be able to figure it out. So I'm almost tempted just to put it out there. So I'm gonna first talk to a senator, believe it or not, first. Because this is going to get swept under the rugs. So I'm going to talk to a senator first. I'm going to see if any lobbying went on with this senator first, to see if any money went to the senator. And then I'm going to, if no lobbying went that direction, then I'm going to talk to the senator and see if they have any interest in it. If no interest, then I'll talk to the second senator. If they have no interest, I'll talk to a couple of Congress people. And then from there, I'll just throw it at the newspaper and see if they have any interest to make the senators jump to it. And then I'll try to find out people who did not want the bridge to be built and try to ally with them. So this is the art of war. So I'll try to ally with them to see if they'll do it. And then from there, you see the way it works, guys, the way I do it. And then from there, I'll well, no, I guess I should have started first. No, I can't do that. He's dialed in that way because I spoke to them. So I can't talk to the the DOT. That won't work. I can't tell you why. It's just I don't see that going anywhere. I'll try. I don't see that going anywhere. And then from there, I'll just let it ride. I'll let it ride. Perhaps I can. It'll be a big joke from there. That'll be to the extent of the attack. But let's go to this explaining that. This pulling effect, this coming down, this pulling effect created here in the bottom of 11. The foot here, the forces. So for this to work in my theoretical way, I would need to show that when you apply forces in 11, that they go down 10. I think I did that in a video for you guys some time ago where I did a gap. I did my styrofoam product where I put a cut inside right here. Is this the right end? Yeah. I put a cut here. I applied a load here with a load inside here, and you saw it push down 10. So that's my theoretical in real practice model showing that loads down 10, loads on an incline, applying a load in this direction and this nodal direction. So the load would be here, not here. Don't think of it, since this is 11, don't think of the loads here. It was applied in this direction in hundreds of thousands of pounds, which goes in this gusset plate, which applies downward force in 10, I believe, which gives me my pressing force here like a foot, which gives me a lifting force here, which gives me a braking force here. And I'm going to share this with NTSB, guys, and I wish you guys would too. I really like this one. I think it's really worth your time. I'm going to terminate the video. Of course, I can fine-tune a lot of this stuff, but I think, when you see the time, it discourages people. I'm happy with this one. All right. And I could go longer, but you know me. I'm hanging up. Take care. Love you guys. Please press the like button. Please comment below. That's even more important, commenting below.